factoring, and we touched on some quadratic formula for those that were not here. So we're going to kind of still keep going along those same lines for a little bit, and then we're going to move off into different directions, especially talking about graphically. But we're still going to talk about solving. So, and we talked about that in class some today too, about what solutions look like and that they are x-intercepts. Don't forget that there's 4 different words for solutions. First is, well, solutions. They are x-intercepts, so where they cross the x-axis. They're also called zeros, so you'll see zeros quite a bit, and roots. So be prepared for any of those words. Okay, so was number 2 on your release items we talked about today that said solutions, and it really just wanted you to find the x-intercepts. So it really wasn't that hard of a problem if you just know that. Okay, yesterday I said we talked about factoring. That was one way that we found solutions. And we talked about quadratic formula. Now, quadratic formula obviously can only be used on quadratics. I feel like that's kind of duh, but maybe not. I don't know. So, factoring quadratics, what we've been over. You obviously know that you can graph. So that's another option. Some people would tell you could look at a table, generate a table. Well, I figured just look at graph, but whatever makes you happy. And then the last way, the one we're going to go over today, it's not as well known, and I'm going to be honest, for solving sake, it was not my go-to by any means, but it's something we're going to have to go over to find for vertex form. So I'm going to go ahead and introduce it with solving, and then we'll go from there. So the other way is by completing the square. So we're going to start out with completing the square since we've already been over factoring quadratic formula, and you know what it looks like graphically, I think, by this point. So I'm not really stressed about that. I would just make something up, and there's no telling how bad that would go. So we've seen how it can happen, okay? Okay, so let's just do, and this we're going to solve by completing the square. X squared plus 6x minus 8. Not to solve. It's technically required in like putting in a vertex form. There is ways around it though, like you could technically just find the vertex and then plug it into the form. Like we did. Right, like we talked about in 4th period today. So like on this, if you're talking about like that test wise for the, that's coming up, could you find ways around it? Definitely.
Yeah, so they're not going to show us like little stupid little square thing all drawn out and all that
right.
Stuff. And like which
the only thing they could possibly do where you'd have to know like the process is they may give you like, this is somebody's work for completing the square. Where's the mistake? So I mean, they have done that before. I don't know if I'm completing the square per se, but so
their problem.
Yeah, that's the only way I can really see where you can't find an out on it. And then good luck, God bless, I guess, if you don't know how to do it. So. Want to say do is actually make the square that you're going to complete. So the square that it's referring to is the perfect square trinomial. To be a perfect square trinomial, so you can always test and see if it already is. If it is, it's really easy to do. You take that middle number, we call it b, because remember A, B, C stuff. So you take b, you divide it by 2, and then you square it to complete the square. Okay, Well, 6 divided by 2 is 3. Squared is 9. Obviously, that's not negative 8. Okay? So we need to complete the square, meaning we need to get 8 away. So I'm going to move 8 to this side. And I'm going to have x squared plus 6x. And I'm going to make a plus blank and put in that 9. That would complete the square. But whatever I do to one side, I have to do to the other. So I have to also add it over here. Is there any questions about that so far? I added it to the right. Well, you could have technically, you mean like, could I put an equal here and put it over here? Yeah, it wouldn't have mattered as long as it's on the other side of an equal sign. Because this is invisibly equal to 0, right? So I just moved it away to where I can complete the square to be separated. Okay, but it doesn't matter which side you put the equal on. I just work from left to right. It's the way I do stuff.
Is that yours? For anybody who's in this room? No, I think someone before is off.
Okay, so is there any questions about this so far?
I thought you were asking to drink it.
Well, supposed to drink it. Good luck with that roulette.
Okay, so 8 plus 9 is going to give us a 17. Now, x squared plus 6x plus 9, the reason why I did this whole thing, why I decided to complete the square, was because you could factor a completed square, a perfect square trinomial, quite easily. You take the square root of the first term, which is just x, the square root of the last, which is 9, or which is 3, and then the sign in the middle. Yeah. Square root of the first, square root of the last, sign in the middle. If it helps, you can also take the square root of the first, just put an x down because you're used to doing that, and then take the middle thing and divide it by 2.
Okay.
Either way it works, because 6 divided by 2 is 3, right?
Yeah.
So either way.
I just don't understand why that works.
But it becomes squared, and I'll show you out here, it's x plus 3 squared, right? That means it's x plus 3 times x plus 3. You okay with that?
Yeah.
Well, if I pull it back out to check to make sure it worked, x times x is x squared. X times 3 is 3x. And 3 times x is also 3x. And then 3 times 3 is 9. So it makes my 6x, and then it gives me my 9 because of that half thing. The reason why it worked is because we divided by 2 and squared it, which is the format that this would have done.
Those mathematicians are smart people.
They're geniuses.
Yeah.
Okay. Any questions about that? Okay. From there, you're just going to solve. So how do you undo? See, this is why I shouldn't make up problems because I made up this problem. See, I told you it doesn't go for you.
I trust you.
You shouldn't. It's not going to be a perfect number. It's fine though. We need to solve for x. What was the first thing we do to solve for x?
Yeah, but so.
Awesome. How?
You square root it first?
Yeah, I have to get rid of the squared, so I have to square root both sides. Remember, when we square root both sides, we put a plus or a minus. So square root plus or minus square root of 17 is what I'm trying to say. And x plus 3 over here. Now what do we do? Subtract 3 minus 3 plus or minus square root of 17. And that's your answer. You have x equals. Technically, could you have looked up, done quadratic formula on this? Well, yes. There would have been probably quite a bit of reducing though in quadratic formula. So that's the good news about completing square. It takes out your reducing. So if you struggle with that, but you can do this process, then complete the square on it. Okay. I would suggest don't complete the square if the middle number is an odd number. Okay, because that's when you get fractions and it's not going to get pretty because you got to divide by 2. I know second period and third period solved a table, so I don't have a problem. Questions about that? Okay, so that's just another way to solve with completing the square. The reason why I'm showing you completing square is not really because of that, but because I can apply those same things to just switching it to vertex form. Okay, so if instead I said, hey, complete the square or change it into vertex form. So alternate question, change to vertex form. I want to use the same example that we just did so you can kind of see a side-by-side comparison. I would have y equals x squared plus 6x minus 8. That would be my standard form. If it was in factored form, multiply it out before you start switching it. I would move 8 over, so y plus 8 equals x squared plus 6x. So my first step is still the same. I still moved 8 over, right? Nothing different. Yes.
Can you write an example, not an example, but like the formula for the vertex form off the side of the formula?
Mm-hmm.
Okay.
So y equals x, or a minus x minus h squared plus k.
Oh, okay, that's simple.
Okay, which if you kind of look up here, you can see that
Yeah.
kind of happening. Okay, so then I say, well, y plus 8. I have to put in those plus blanks just like I did up here. I'm still completing my square. So I have x squared plus 6x. I still do the divided by 2, and then I square it to get 9. So it becomes y plus 17 equals x squared plus 6x plus 9. I need to give y'all a second. Yeah, sorry.
I did say we were gonna get that time.
Okay.
Yes.
It's the same up here. Remember, we took that middle number, divided by 2, and squared it. So I took 6, divided by 2, and squared it. Okay. Yet again, if you compare what we've done here to what we did up here, I've not done anything different. Okay. Other than I had a y there instead of just a 0. Okay. So now I'm going to factor it the same way. I'm going to take the square root of x squared, which is x, the square root of 9, which is 3. So it's x plus 3 squared. Once you do that and you do the factoring part, you're just going to get it to where it's y equals. So I'm just going to move 17 over. So y equals x plus 3 squared minus 17. And that's my vertex form. Okay. If I asked you what the vertex is, can you tell me what the x value of the vertex is?
Where are the P's and Q's in this? Didn't you say vertex form?
Instead of p's and q's, it's h and k.
Oh,
It's okay. Right, the 3 becomes the x, if remember, if it comes out of those parentheses, it becomes negative. It changes signs, whatever it is. So it's negative 3 and then negative 17. Okay. So I could ask a couple different things. I could have given you this problem and said, hey, what's the vertex? And if you don't like finding it on a calculator, which some people really hate using a calculator to find vertex, I'm not a big fan of it, to be honest. You can use this format to do it. If I just said, hey, what is the vertex form, then you have to do this. Or you could do the opposite. You could go on the calculator, do what I hate, and find the vertex, and then plug it into the format. Okay. Is there any questions about that?
how do you find the vertex on calculator?
Remember when we did the min
Oh, yeah,
earlier?
okay.
So you're okay with that?
Yeah.
Okay.
So the vertex is like
The minimum or the maximum.
okay. All right. Let's see. But you hate
That annoys me, to be honest.
Yeah,
I'd rather do the algebra.
I had a
but
lazy teacher.
Obviously, I like algebra, so it's kind of my thing. Any questions about completing square? Do we want another example? Okay. So let's get one more. And if you want another one, I'll give you another one. I'll give you as many as you want. We're gonna just do it to where we're solving for the actual vertex form instead of solving, because I thought solving you have so many options, but vertex form you have less. So we're gonna put it in vertex form, and you're gonna let me find a good example because you don't want me to just make up a scrappy answer. Oh, here it is. Ha, ha, ha. Found it. Let's do y equals x squared minus. Oh, that one's messed up. Just kidding. Y equals x squared minus 8x plus 12. Yep, we're going to put it in vertex form. So if you kind of want to work ahead to see if you can do it, that's fine. And then I'll give you a minute to look at it. I am going to go ahead and start working it out. So for those that need that step by step, that's fine. I do check and look and see if it actually is our perfect square trinomial. Because if it is, then my work is pretty much done. I just factor it and I'm done with it. But x squared minus 8x plus 12, negative 8 divided by 2 is negative 4, squared is positive 16. So obviously that's not correct. So I have to move it over. So y minus 12 equals, and then I have x squared minus 8x. Then I make my blanks to complete my square. And yet again, you take that number, so negative 8, you divide it by 2, and you square it. And whatever you do to one side, you do the other, so you add it to both sides. Are there any questions so far? Okay. So then, on this part, I'm just going to combine them. So y plus 4 equals, I have x squared minus 8x plus 16. We've made it a perfect square trinomial, and we did that so we could factor it to that perfect square. So I have x squared, so it becomes x, and then the 16 or the negative 8, either way you want to do it, comes to the negative 4. Then I'm going to subtract 4 on both sides. So y equals x minus 4 squared minus 4. And that's vertex form. Is there any questions?
So that's finding vertex form.
Yep, it's finding vertex form. And if I ask you what the vertex is, what is it? Close. Yeah, positive 4, negative 4. Remember, when it comes out of those parentheses, it always switches signs. Okay.
So finding what was the name that you're finding for it? Vertex form or vertex?
Yes.
Finding the vertex.
This is vertex form.
And that's where the vertex would be at on the graph.
This is the actual vertex of the graph. Yeah. See, any questions? I'm going to show you real quick. I'm not going to spend a lot of time on it. If it was already like this, so x squared plus 5x plus 20, no, not 5, 10. plus 25. So if I did x squared plus 10x plus 25, and I checked the very first step, like I told you, for it being already perfect square trinomial, well, 10 divided by 2 is 5, and squared is 25. So it is the perfect square trinomial. So I don't move anything over, because that's just going to cause more work. There's no point in that. So I go ahead and factor it, and I get x plus 5 squared. And that is vertex form. Okay. What would your x value of your vertex be? Yep, -5. What would your y be if it's not there? Yeah, 0. Okay. That's why I always check first, because if you had moved over that 25 and then you'd add 25 to both sides, you'd have been kind of upset at yourself. I mean, or you wouldn't even notice and you kept working and. Okay.
Is it perfect? You just skip that stuff.
Do what?
So if it was like a perfect square.
Right. You basically just skip all the way down to this one. And then you don't have to move anything over. So look, I mean, because, hey, it's done. It's done. It only takes 2 seconds to look. So,
Yeah. Okay. So if they have an example problem and the kid does it, can we call them stupid on the test?
you can write it on the book, but you cannot write it on your test.
Do they ever look at that? Because
Interesting.
I'm really sassy on those.
Oh, they
all the
don't.
time.
It's on computer now, so it doesn't even matter. You're just clicking.
Oh,
And
really?
the answer is no.
They don't? My life is ruined.
I'm so glad I could ruin somebody's life today. That was my goal.
Alright, because I would put like duh and stuff like that all the time in the book.
You're such a sweetheart.
Yeah, I mean, they did look at them. They didn't know that was a duh problem. And if I got it wrong, then I was duh. I thought that was creative. That was just
You're
so bad.
hilarious.
I'll go back. Okay.
Are we done now, Luke?
Emotional.
Okay, good. Okay, and back. I do want to take a second and look at this example. The standard form of this one was y equals x squared minus 8x plus 12. The vertex form, we found that one, is y equals x minus 4 squared minus 4. The factored form would be the other way to represent it, okay? So factored form, I would have to factor from yesterday or from if you just knew it whatever way. Two numbers that multiply to get 12 but add to get -8 would be -6 and -2. So it would be y equals x minus 6 times x minus 2. And so that's the 3 main ways to represent this quadratic, okay? They each offer their own good points. Standard form is good because you can just go ahead and put it into quadratic formula or something like that. You can also switch to standard form to vertex form without any complication. Vertex form obviously gives you the vertex, so that's good. And factor form tells you your x-intercepts. So there's 3 forms. Make sure you know them. Make sure you know what each offer to you. Okay? You can switch between the 3 different forms in different ways. You can multiply out the factor form, get standard form, and then obviously you can complete square to get vertex form. Vertex form, you can multiply it out and then subtract the 4 to get to standard form, and then actually factor it to get to factor form. So always work. I know. I got it. I remember.
Have that degree, so
I know. I'm
Yeah.
amazing. I'll see you tomorrow.
Yeah. What's fun?
Any questions? Okay, so we've got 3 forms. We did that. Oh, we're halfway done. Does anybody still need to see this before I move it? Okay, so we're going to kind of switch gears a little bit and get off of like the actual solving for x-intercepts and stop talking about some algebraically. We're going to transition it by talking about multiplicity of zeros. So we talked about x-intercepts and zeros, which are the same thing, right? But we haven't really touched on multiplicity of zeros. So multiplicity of zeros or x-intercepts if you prefer to call them. I don't really care what you call them. We kind of touched on this when we talked about functions and we did that functions family album stuff. I am going to show you Desmos. I just have to figure out how to switch it to where it can see Desmos. Give me a second to think through it. Oh, I got an idea. Does anybody need more time to write that down? Okay, that's fine. Everybody got it? Nobody's screaming at me. Okay. So we are going to go to this, and we're going to tell it to stop sharing. And we're going to go here. And we're actually going to share my entire screen this time. Okay. That's kind of creepy. Okay. Go away. Well, I have to actually pull it back up and go to Desmos. So Desmos. We talked about it when I told y'all how things kind of flatline. Remember I told you like x to the power 26, and I showed you visually what it would do. For those that don't remember, I'll show you again. If my computer will operate, there we go. So x squared is that parabola, that U shape. You've seen it a billion times. You know what it looks like. X to the power 20. Oh, well, actually, let's do x to the power 4. X to the power 4 looks very similar. If I put them side by side, so if I put x squared also on there, you would see difference in how fast it goes up in the steepness. You would also notice that x to the power 4 seems to kind of flatline just a little bit. It's even more so if I put like x to the power of 26. You see where it really flatlines. It's not that it really happens at like 1 or anything, though it looks like it's touching 1 on the x-axis. What is happening is 0 is happening 26 times in that moment. And the only way your computer knows how to show that is to basically flatline it out. Okay? The multiplicity of 0 in that moment is 26. Okay? So however many times an x-intercept occurs is its multiplicity. And what I mean by that is at this moment, I can get rid of that. We have x minus 4. We'll say x minus 4 times x plus 7. Okay? That's our graph. We know factored form gives us our x-intercepts. No big deal, right? Each of these have only happened once. If I put x minus 4 times x plus 7 to the power of 3, we'll look at negative 7 and what happens. It is happening 3 times technically. It is considered to hit it once when it comes up, hit it back down again, and hits it as it goes its final turn. Okay? It kind of looks like an x to the power 3 function, just in a mini form. So if I did x to the power 3 right here, see it has that same shape to it? Okay, that's the similarity. So its multiplicity is 3. Anytime it's odd, it's going to pass through the actual line. Anytime that it's even, it's going to touch it and then come back up, or touch it and go back down. Either way, depending on if it's upside down or right side up. So if I did minus 4 and I put it to the power of 6, okay, well, this one, yet again, it touched it and it went through on the negative 7 because it's odd. But at the 6, it touched it and then it came back and turned. Okay, evens will always turn back around. Because think about it, this is considered one touch. If they can't see my hand. It's considered one touch as it comes down, and then it's considered another touch as it goes back up. Okay? Well, when it's to the power 6, it's considered that it went down and came back up and went down and came back up and went down and now come back up again. So in its eyes, it's happened a lot, just at the same little number. Does that make sense? Weirdly, in a very odd way, I know, but okay. So the multiplicity at 4 would be 6, and the multiplicity at negative 7 would be 3. And all you're basically doing is looking at your exponents, right? Even if I threw an x in front of it, that'd be x equals 0. Notice how it now goes through the origin. And that happens one time. So my multiplicity at 0 is 1. So you would have to list each of these out. You would have to say x equals 0 is multiplicity of 1. X equals 4 is multiplicity of 6. And x equals negative 7 is a multiplicity of 3. Yes.
Would they ever give you a graph and like ask you for the exponents to go? Like,
No,
kinda
they
like
may
a
ask
table?
you if it's even or odd, but they can't ask you if it's, is it 6 or 4,
Like,
because of the fact that you can't tell.
yeah, that's
So yeah, even or odd is very possible, but not the actual number. They could give you one and say, is this a possibility for a function? So like they could give you several of these and say, could this work for this graph? That's possible. Any questions? Okay. So let's switch it back to where I can't screw it up. Which just kind of, okay. How do you stop sharing? Stop sharing. I don't even know what these people see whenever. Even better yet, they get to hear me talking about it.
Oh, is this for a video?
Yeah, this is their video.
Maybe I have to invest-
Oh yeah,
Oh my goodness.
they can do every little thing Luke said and everything.
Oh wow.
So now we talked about kind of how it looks like with multiplicity. Um, it also kind of covers in behavior. We kind of saw that when we did like x to the power of 3. You saw it went up, or it started this way and went this way, right? And we talked about in behavior before. I know that we've done that very recently, but it never hurts to remember. In behavior is literally how it just behaves on the ends. It's exactly what it says. I don't care what's happening in the middle. Now, unfortunately, there's a lot of confusing ways they can say this. They can say, hey, what's the end behavior, which is a pretty straight up answer. And you would say, this one's going down on the left and up on the right. Okay? They could also say, what is the end behavior as x approaches negative infinity? Okay? Well, we know that x approaches negative infinity means going to the left, correct? Well, it is going down. So you would answer down. Okay? They may even say a little bit more specifically what happens to y as x approaches negative infinity. And the answer to that would probably be written in form as y also approaches negative infinity, which means y is going down. Is there any questions about that? Okay, so be prepared to read it. Okay, when it says approaches infinity or negative infinity, if it's approaching infinity on x, it's going to the right. If it's approaching negative infinity, it's going to the left. If it's talking about y approaching negative infinity, it's going down, and then y approaching positive infinity is going up. Okay, and if you get confused, just think about it. You know what infinity and negative infinity mean. You know what x and y mean. Just take a second to assess it and figure it out. Okay. So the general rule of end behavior, though, if you think about an x squared graph, we know that it does that U shape, right? But if I said negative x squared, it would flip upside down. So, right? Okay with that? So I'm going to draw a little chart for end behavior just in case you need it. If you need it, great. If you don't, okay. I'm going to be honest. It's one of those things, I don't know the rules by heart. I sit there and think about the graphs of the common things I do know. So this is positive, negative. This is odd and even. If it's odd and positive, it's going to go down on the left and up on the right. If it's odd negative, it's going to flip direction. So this graph would actually end up going like this. So it would go opposite. It would go up on the left and down on the right. Even positive is up, left, and upright. And then even negative is down, left, and down, right. Is there any questions about that? I think most of you can do that. I'm not really stressed about you being able to tell me in behavior because if nothing else, you can always like type in the thing and look at the graph. I'm more worried about them being able to interpret what they're saying by X approaches and stuff like that. Because sometimes I know when you're in the middle of a test and you get to question, 33 and you see X approaches, and by that point you just want to give up and be like, exactly. So screw this X approaches. I'm done. So, but try not to do that if you see it because it's really not that bad if you just take a minute. So it could take like the really easy question and end up being wrong when you could have gotten that. Okay, does anybody still need to see this before I move it? Okay. So now we're going to talk about graphic symmetry. So and this one's probably one that y'all remember a little bit better because we did this right before break. Right before break. Or if you're looking at me like I'm crazy, as certain people are, you could not remember it all. That's totally fine too. So you have two types of symmetry options. It's either even or odd symmetry. Okay, so even and odd symmetry. If it doesn't fit either one of them, then it's just neither. Okay. So even symmetry is symmetry about the y-axis. Odd symmetry is about the origin. Okay. Remember we talked about the y-axis and it be mirror images. Okay, so that's talking more about your standard parabolas like that. Okay. About the origin is a little bit harder to see. Whatever happens over here, so on this side of the origin, notice I did this, it's flipped opposite on this. Now, realize I'm not a perfect drawer. It's supposed to do the same exact thing, like at the same rate and everything, but I was not that good. I'm sorry. Okay, did my best. Don't judge. Okay, so visually sometimes you can just tell, but I'm also going to talk about how to find that algebraically. So if it is even, the trick is just that it has even exponents, all even exponents. And you can actually add a number at the end. Okay, and I'll show you why the trick works. So and/or constants. Remember, constants are just numbers at the end. this works, this little trick memory thing works because with evens, I should be able to plug in negative x for every x and get back this original function. Well, what happens if I square a negative? Yeah, it's positive. Anytime it's an even number, if it's power 4 to the power 6, whatever it may be, if it's even, it's going to make it back to a positive every time. So that's why it gets it back to the original. And a constant, just a plus 7 at the end, well, that doesn't really matter because I'm not putting a negative x attached to it, so I can't change the sign with it. So an example of that would be y equals x to the 8 minus x to the 6 plus x squared. I'll do 3x squared just for fun, mine as well, minus 5. Okay. Well, if I plug in negative x for each of these, so negative x to 8 minus negative x to 6 plus 3 times negative x squared minus 5. Each of these negative x's, because they're attached to an even exponent, just become x again. So x to the 8 minus x to the 6 plus 3x squared minus 5. So it ends up coming back to the original, so it's an even function. Okay. So you might need more time to write that down before I move to odd. Okay, so odd, the trick is I have odd exponents. Makes sense. The only thing is I cannot have any constants. So no constants. Okay, so you have to have a variable of some sort. If it's just a number, it's not going to be odd. Okay, you're going to do the same thing. You're going to plug in negative x for every x and get the same function but with opposite signs. So every sign will change. If every sign does not change, if only one sign changes, then it doesn't fulfill either requirement and it's neither. Okay, so example of that would be y equals x cubed minus 5x. Okay, so I plug in negative x. Odds cannot change the sign back to positive. It's always going to be whatever, it's always going to keep it as negative. So it's negative x cubed minus 5 times negative x makes it plus 5x. So every sign changed. I cannot have constants because if I added like a 2 to the end of that original one, it needs to change signs. It can't change signs if it doesn't have an x to change signs. Any questions there? hopefully that reminded you what it was. Ring some bells. Does anybody need more time to write before I move it? That's fine. We're going to one more little thing to talk about, and I think we're done.
One constant that would be constants, it could be
On odd, they couldn't have any constant on it. So they couldn't, any number that you added to it, it would still, because the idea is that every sign has to change. If it's just a number at the end, it doesn't have an X attached to it that can make it change when I plug in negative X. So I can't have it. So if I had a mixture, if I had like X to the fourth minus X cubed plus 2, that would change. This would not, or sorry, this would not change. That would change, and this would not. Because it's mixed, this would be neither. It would not have any kind of symmetry that we can identify. Okay, so the last thing we're going to talk about, and we'll take it a second, is increasing and decreasing intervals. Okay, so increasing and decreasing intervals. It is exactly what it sounds like. It is telling how a graph moves. Okay, so I'm going to make up some numbers here in just a second. And say this is -8 and this is 2 and 1 there. Okay, increasing, decreasing intervals, it's like you're the roller coaster. And you're telling me when you're going to rise and when you're going to fall. And you always read it from left to right. Okay, so my roller coaster's moving. Right now, what is he doing if he's moving? Increasing or decreasing? Increasing, right? So from -infinity to -8, it's increasing. So it's similar to domain, except for I'm not saying what's happening all the way from left to right, I'm doing it in pieces. Okay. Then I'm going from -8 to where for my decreasing? Not, it's positive, but yeah. So -8 to 2 decreases. And from there, from 2 to infinity, it's going to increase again. Any questions about that? Don't forget, before I forget, domain and range. You always look for domain all the way left, all the way right, and range is all the way bottom to the top. I know we went over some of that today, so I think most are okay on that. Is there anything with polynomials anybody needs me to talk about or go over in any way? Okay, then we're going to end it there.